At our current trajectory, accelerating climate change threatens irreversible ice loss within the next 70 years. At the same time, artificial intelligence requires a computational scale that is currently compounding. Terrestrial data centers continue to expand to meet this demand, consuming gigawatts of fossil fuel grid power. Beyond the power draw, these facilities exhaust millions of gallons of fresh water daily just to keep standard silicon GPUs from overheating. This chart plots the trajectory of our current infrastructure. The rising line shows exponential AI power and water demand, while the descending line shows the finite availability of terrestrial resources. These lines are on a collision course. Solving a climate crisis using an infrastructure model that inherently exhausts the biosphere is mathematically impossible. Kindara's thesis is that the sustainable future of AI compute must exist in low Earth orbit. Moving these systems off-planet requires overcoming two specific engineering roadblocks: thermodynamics in a vacuum and system crash prevention across high-latency networks. To achieve orbital intelligence, we must abandon terrestrial assumptions about solid-state hardware and distributed software architecture. Low Earth orbit is a vacuum, completely lacking the air and water necessary for traditional cooling. Convective cooling, relying on fans or loop loops to carry heat away from a processor, is physically impossible in this environment. Under heavy load, a standard silicon GPU without convection faces an uncontrollable thermal gradient spike. The hardware physically melts. Aside from the thermal constraints, off-planet compute must survive unshielded cosmic radiation. High-energy cosmic rays penetrate the solid lattice structure of standard silicon chips. This schematic shows a cosmic ray striking a solid silicon transistor. The ray disrupts the electron flow, causing the logic output to flip from a 0 to a 1. These localized hardware bit flips cascade into unmanageable logic errors across the system. Standard silicon is physically incompatible with the space environment, ensuring failure through either thermal melting or radiation-induced crashes. The hardware solution requires replacing silicon with nanoscale vacuum channel transistors, or NVCTs. Comparing architectures, NVCT replaces the solid silicon channel with an empty vacuum gap. Electrons shoot across this empty gap without resistance. With no physical lattice, cosmic radiation passes straight through. The electron flow remains uninterrupted, guaranteeing complete immunity to bit flips. But even with radiation immunity, the system must still shed heat in a vacuum without water cooling. In space, heat dissipation is governed by the Stefan-Boltzmann law of radiative heat emission. Radiative emission scales exponentially to the fourth power of temperature. Plotted here, standard silicon fails at 100 degrees Celsius, yielding minimal radiative potential. NVCTs operate safely up to 500 degrees. Pushing up this curve unlocks a massive 5.5x increase in radiative efficiency per square meter. Despite these temperatures, NVCTs remain compatible with standard binary logic and 3D stacked magnetoresistive RAN. Operating at 500 degrees allows high-density compute to natively cool itself in a vacuum, entirely eliminating the need for massive radiator panels or liquid loops. Deploying AI across Earth-to-space constellation networks and edge nodes introduces extreme network complexity. Moving tasks between fragmented, high-latency nodes often leads to AI amnesia, the loss of contextual memory that results in system hallucinations. Kindara governs this space-to-Earth continuum through the Oracle State Engine. This topology diagram shows the engine's foundational principle, the strict decoupling of compute nodes from state memory. Compute nodes function as temporary processing engines, while the actual context of the AI agent lives in an unshakable database layer. Fault-tolerant circuit breakers sit at every boundary within the interface to validate data flow. If an orbital node encounters an anomaly, the system identifies the failure in milliseconds. The circuit breaker intercepts it, preventing corrupted data from reaching the central state. The interface rolls back to the last verified state and reroutes the task to a healthy node. Separating compute from state allows the system to maintain continuous AI execution, passing uninterrupted intelligence across a fragmented orbital constellation. Sustainable off-planet compute requires a tandem redesign of both physics and governance. We must use NVCTs to exploit the vacuum for radiative cooling, rather than struggling to maintain terrestrial cooling standards in space. We must separate compute from state memory to remain resilient against the fragmentation of deep space networks. This layered approach allows orbital constellations to power a seamless experience on Earth, where the software state remains stable even during hardware-level interruptions in orbit. The planetary runway is narrowing. Current data centers carry a footprint that Earth's biosphere cannot sustain long-term. Moving this computational burden into orbit allows AI to scale without exhausting our terrestrial power grids or freshwater reserves. To preserve our planet while advancing intelligence, the future of AI computation cannot remain terrestrial. It must go orbital.